All right, so I'm going to talk right now a little bit about what a fundamental matrix is. Really, it's nothing new for you if you already know how to do eigenvalues and eigenvectors. It's just looking at them in a little bit different way. I guess what I mean, or not look at them, but like putting them together in a different way. So I'm going to be general at first, and then I'll give you a more I'll give you an example. So if I have x prime equals ax, and we'll assume 2 by 2a for now, and x1 and x2 are the solutions. What I mean by that is like the eigenvector times the e to the eigenvalue. Then my FM, my fundamental matrix, is just it's called an augmented matrix. It's what you do when we do REF. But it is x1 as a column in one matrix, and x2 as a column in within that matrix as well. So this has two columns. Notice this would be a too tall vector, So if this is too tall and that's too tall, it's too wide. If A is a 2 by 2, then this is a 2 by 2. So let me give you an example of one of these. Let's take x prime equals 1, 2, 2, 1, x. You could pause this and go ahead and do your eigenvector work to get two solutions just as practice. I'll go through it kind of quickly. I got lambda squared minus 2 lambda. That's the negative trace. And then my d is 1 minus 4. So that's minus 3 equals 0. If I were to factor that down, I would get and set equal to 0. I would get lambda equals 3 and negative 1. So let me come over here. Lambda equals 3. And I'm going to subtract it along the diagonals. That gives me negative 2, 2, and 2, negative 2. My vector for that is 1, 1. I'm going to take lambda equal to negative 1. That's going to give me a 2, 2, 2, 2, which gives me a vector of 1, negative 1. So, my x1 in this case is, usually we write x equals and then c1 and c2s and stuff like that. Another way to talk about that would be to say x equals c1 x1 plus c2 x2. How could I, what am I trying to say? Well, x1 in this case is just 1, 1 times e to the 3t. x2, and it's arbitrary which one comes first, is 1, negative 1 times e to the negative t. So, what's the fundamental matrix? Well, I want you to see that I could rewrite x1 as e to the 3t, e to the 3t. If I distribute this, if I distribute this guy right here into there and into there, right, then I would have two of those terms. And x2 would be e to the negative t positive in the top, and then negative e to the negative, t in the bottom. So these guys right here are the two pieces that I'm going to use in my fundamental matrix. All right, Fm equals e to the 3t, e to the 3t, and then e to the negative t and negative e to the negative t. A couple things to point out about this. One, this is a square 2 by 2 matrix. That's the first entry, that's the second entry, that's the third entry, that's the fourth entry. There's no addition horizontally here, right? It's just this guy and that guy in one column, so those two, and then this guy and that guy there in the other column. I could have had these switched, right? I could have written that one first and this one second. That would have been a different fundamental matrix. I could have chosen, we chose the vector 1, 1 here because it was like obvious. It's the easiest one to do. I could have chosen 2, 2. And if I had done that, I would have had a 2 here and a 2 here. I could have chosen 4, negative 4, and gotten 4, negative 4 there. What I'm trying to tell you is that there's just an infinite number of fundamental matrices. So there's usually a easiest, right? The one that we chose a moment ago, originally there, or the flipped version of it, the e to the negative t's on the left side and the 3's on the right. But there are an infinite number of fundamental matrices. There is a general way to write fundamental matrices, but we're not quite ready to do that. I guess the last thing I'll say is sort of what I said in the beginning, which is that the fundamental matrix is just another way of writing the solutions that you already know how to do with eigenvalues and eigenvectors, right? Normally you would write x equals c1 times 1, 1 e to the 3t plus c2 times 1, negative 1 e to the negative t. And that's like how we write the solution. I can actually manipulate this. I can manipulate this so that it is exactly what I have here, but I'm not going to do that quite yet. Anyway, hope that makes sense. And it seems kind of silly why we would do this, but like there are tons of reasons why. It makes a lot of other things that we do easier. It's just a way to store the solutions to a system of differential equations in a way that is useful for other things. Forgot one pretty important point. We typically don't write FM. We write a capital X whenever we're talking about a fundamental matrix. So the standard notation for fundamental matrix when you get it from x prime equals ax is that capital X. So that'll show up a lot as we move along.